I want to say a few things about Q-learning. So let's see what we have learned so far. In value iteration and in policy iteration, an agent learned a policy before it even took the first step. Okay, so what we're going to be doing different here in Q-learning, we will explore, as we explore our world, we will update our policy. And so this is a form of temporal difference learning. So the idea is that, we're born, we're placed in different environments, and we need to act, right? A lot of times the environment requires actions of us, and so we sort of like do it, right? And then we learn from the environment. We sort of get feedback. Again, there are other ways of learning things. A lot of times we pay attention to what our parents are telling us and other people that we respect. So that way, we sort of like know what to avoid and what to try. So before we, so I'm going to try to understand this algorithm a little bit better. It might be helpful to have a look at an animation. So I hooked that up on our website. It's the animation by that is written by the same people who developed the value iteration animation that I've shown you before. So let's have a look at this. So the idea is that initially we don't know anything about the world. We're being placed in the world somewhere and we're going to try it. So let's see. It's the same world for your reference that we have seen before. I think there's a 0.3 over here and a 0.10 somewhere over here. Let's see if we get lucky. Yep. All right. So this is an absorbing state, and the convention in this animation is that if you're in an absorbing state, you're put randomly into one of the four corners. And so let's go to the left and down again, and right, and right, and right, and down, and left, and down. So we learn new things. So as I go on, I went down, and I got a reward of 3. How we do the reward calculation, we will see in a moment. But so notice that we now kind of like learn that, oh, okay, well, push them to shove, so like prefer these two rather than these two. Let's see where we can find the one down here. Come on. There we go. So going to the right gave me a reward of 10. Again, this was an absorbing state. I'm being randomly played into one of the corners. So as you can tell, we're exploring this world, getting feedback as we go along. And this obviously takes a long time because we're doing this in real life, or in real time. The other ones, again, I mean, they ran for a long time too, except there wasn't a simulation associated with it. We first calculated the value matrix and read off a policy, or we sort of like iterated through policies, improving them until there were no more changes, and then we started acting. So it just takes as much time as this one over here, except there's some differences. So let's see whether we can explore them. The first thing to realize is that we do not learn a utility function and we do not learn a policy. Instead, what we're going to learn is we're going to learn pairs consisting of situations and actions. So we learn the value of an action in a given situation. That's very important to realize. If I go back to this one over here, we learned that the action of going to the right in this state has a value of 10. The action of going down this state has a value of 3. That's all we know. So that's what we're going to learn. We're going to learn these state action pairs. So in order to understand this formula and the way we do this thing, it's helpful to do a little bit of an exercise. So on the website, I posted a link to this thing. So here's this thing. So there's the worksheet, and yes, there's also a solution. This one here is a link to the code that I just demonstrated to you. It's the same warning or disclaimer that I said last time. These people have been around for a long time. They're very reputable. You can't run applets anymore, so you have to download them and run them on your own computer. So at your own risk. So let's have a look at this worksheet. And we sort of want to explore this formula that I expressed to you in a moment ago that's also displayed down here. We want to understand the components of this expression down here. So this is a different world. Again, actually, this one is from the book on Poole and Mackworth on AI. So we have, let's see, 6 states, and we have 4 different kinds of actions. And so let's understand the states and the actions before we look at the state transition functions here. So up C is up carefully. The agent goes up except in states S4 and S5, so from 0 to S2, from S1 to S3. And so the going up in these two states is fine. Going up in these two states is fine. But over here, going up is a reward of -1. Actually, the reward is always -1. I apologize. Except in S4 was simply, if we try to go up, we stay here, and same thing over here. Going right. In S0, S2, S4, going right, we will go right. We end up in 5, 3, and 1 correspondingly, and there's a reward of 0. If we try to go right in S5, S3, or S1, there's a reward of -1, and we stay still. Left, the agent moves 1 state to the left in S1, S3, S5, so S5 to S4, and so on. And but it's a little bit different in these 3 states. So if we try to go left in state S0, we stay in S0, and there's a reward of -1. In state S2, if we try to go left, there we will stay in S2, and there's a reward of -100. Not much of a reward, eh? And in S4, we get a reward of 10, and we end up in state S2. So a little bit different transition function over here. Up. So here we have a stochastic transition function. With 0.8, it behaves just like up C, except the reward is 0. And with probability 0.1, it acts as a left, or with other 1.1, it acts as a right. So let's go through a pretend trace of this environment. So we'll start in S0, and we determine, let me do up C. Okay. So again, this is a book. This is an exercise. So obviously they sort of made up something. The key thing is we want to understand how we calculate the Q function here, state action pairs. All right, so let me make this a little bit larger so we can see a little bit more. So we in state S0, we're going to do up C, it turns out. So the action in state S0 is up C, the reward is -1, and we're going to end up in state S2. Just remind you, in S0, we go up, there's a reward of -1, and so this is deterministic, not a stochastic transition function. So how do we calculate the -02? Well, the transition table is empty, so all these values, this is 0, this is 0. So all we have to deal with is the reward, and so the reward is -1, and then we have this tuning parameter alpha, which is 0.2, and the gamma is 0.9 again. So all we have is 0.2 times -1, so that's how we get the -02, or the -0.2, I should be precise. So that's the value that we got just calculated. All right, so now we're in S2, and we decide to go up. And so up with a probability of 0.8, it acts just like up C. So we are going to be in state S4, and the reward is 0. So what is this value over here? Well, just like we have seen a moment ago, 0, 0, reward 0. So we have some concrete information. It is 0. Fantastic. We learned something new. Now, for the purposes of learning, we imagine that, the next action is to go left. So we're in state S4 and we go left. So if we're in state S4 and we go left, we end up in state S0 and we get a reward of 10. So that's what we see over here. S4 going left, reward of 10, and the successor state is S0. So how do we determine this value over here? All right, so this one is 0. This one here, we'll sort of ignore that for a moment. And so we'll just sort of simply pretend it's 0. And I'll explain that in a minute. And the reward is 10 though. And the tuning factor is 0.2. So 10 times 0.2 is 2. So what we learned over here is that in S4 going left has a reward of 2. And again, as we go along, these values will increase because of this addition over here. All right, so now let's actually have a look at how this one works by looking at this one over here. So we're in S0, and we again decide for various reasons that we want to do up C. And so the reward is the same, -1, and we always end up in state S2. So let's explore what's going on over here a little bit. And so, what we're going to do is we're going to look at the successor states, the successor state, S prime, and the actions that are available to us there, and what the values are. So successor state, actions, we're going to look at our table, and we sort of say, okay, which action gives me the highest value? Okay, all right, so where are we going to be? We're going to be in state S2. Okay, highest value is 0. Again, good to know because it could be negative, right? So that's how this thing works out. So this one turns out to be 0, and the tuning factor, again, you know, it doesn't matter. So what we're going to do then is we're going to look at a reward of -1, and we sort of like see, do we need to subtract anything? So what is the current value? Oh yeah, it's -0.2. So we subtract that from our R, and so that gives us -1 plus 0.2. That's -0.8. And we multiply that, I'm sorry, with 0.2, so it gives us -0.16. We add that to the -0.2, which gives us -0.36. That's how you can end up with this one over here. Okay. All right. So I briefly wanted to explain, and so what I ask you to do is fill up the other one. So please do it, and then look at the cheat sheet later on, or the solution sheet, just to make sure you understand you get this thing right. So I wanted to say something about this term over here when we calculated this one over here. Okay, so when we calculated S4 left, we technically would have needed to look at the maximum of the table entries for S0. Okay, so it turns out that S0 we only have one entry, which is negative, and so we just simply treat all the other ones. Again, we have other actions available, all 4 of them, and so since they're empty, we treat them as 0. So that's why we actually do take the 0 over here, even though we have a value. We have this value here, -0.2, but since it's negative, we'll sort of like pick any of the other ones that have no values, which we treat as 0. So that's how that one came in. All right, so that's Q learning on the fly. Now, let's see. So I'm sorry. So this is the term. This is the exact same formula that we just explored, and so we'll just like go on. So over here we go until S is a terminal, and then we probably start another episode until we get, well, until we are done with life, I guess. Maybe, I don't know. So a key thing though is if we go back to this thing over here, you know, if we're placed somewhere over here, we just don't know what to do, right? We just have no information. Even over here, well, we never tried any of these things, so how do we know that this isn't 100 or 1,000 or something like that? So it's very important that we don't always simply go by the highest reward. We want to explore things a little bit. And so that's this idea of exploration versus exploitation. So what we have over here, we have a function with 2 arguments, u and n, which is called an exploration function. And what it determines is when we might want to sort of like go with a known value, the utility, and when we might sort of like say, you know, I haven't explored all my options sufficiently enough, so let me do some more exploring. So that's the idea. So we have some sort of NE, which, you know, is say 10 or something like this. And so if we haven't explored something, the frequency count enough, we'll sort of like do some more exploring. Okay, we sort of like look at what are our options. Otherwise, if we feel that, you know, we have explored our options sufficiently, then we simply go with the greedy or the value of the highest utility value. That's it. All right. So the way that works out then is over here, we have some of the same stuff that we have seen before. Okay. And then, so we calculate we update our table, and then over here, this is the function f that we talked about a moment ago, where we have frequency count of how many times we have explored something in state S given action A, and here is the utility of our utility table, and so that's what we're going to do. So we plug these things into a function, and we get something out of it. So I implemented this, and so I have I briefly want to show that to you. It's not as impressive as the other one. So what I have over here is I have a policy. Again, it was randomly initialized. I'm sorry, I have a frequency count and I have a policy. And obviously I also count I determine the values of the transition functions. Let me explain a little bit. This is up, left, right, down. So we went up 0 times, we went left 0 times, so we went right 2 times, so we went down 1 time. So that's the frequency count of the actions from this state over here. So again, I saw like telling you the best policy so far, just like in the other animation. So it's kind of interesting to figure out, how do we actually get here? Because this is only after 1 episode. And so we went up, we went right 2 times, we went left 2 times, we went right once, left once. So we most likely started out over here, we went left, we went down, then we went up, then we went left, then we went down, then we went up, then we went right, then we went left again, then we went right again, then we went right again, and then we went right again. So I think that's how we ended up, although I'm not sure I went right twice. So we actually have started over here. We went right, left, did the detour left, did the detour right, left, right, and so on and so forth. So there you have it. It's just fun to explore this stuff. And so now, after 2 episodes again, so you can tell that we explored our world quite a little bit until we went to this absorbing state. And again, so far, our best guess is this utility. And well, going left over here is not that smart, but all the other ones are actually not that bad. And so after 3 steps, so exploring, and so notice after 4, actually, this is not a bad policy, right? I mean, this is just about as good as any other one. Here are the frequency counts. And so we'll just explore this stuff a little bit more. Doesn't change that much. So there you have it. So using the frequency count, and eventually mine cuts out at 10. Alrighty, folks, well, that's it. I'll talk to you later. Bye.